Next, another unit is molecular spectroscopy. In molecular spectroscopy, which is mentioned in the syllabus, in molecular spectroscopy, which is mentioned this topic, electronic spectroscopy and IR, Raman and microwave, some concepts will be mentioned, right? So in molecular spectroscopy, first one is in the electronic spectra or electronic spectra or spectroscopy. Electronic spectroscopy, which is mentioned in the syllabus, molecular spectroscopy. So one is electronic spectra and another is IR, infrared spectra, another one is in the microwave, right? So both three will be combined and molecular spectroscopy, which is mentioned in the syllabus. Listen. So first one is in the electronic spectroscopy. Electronic spectroscopy. This electronic spectroscopy is also called as UV visible spectroscopy or UV spectroscopy. UV visible spectroscopy or UV visible spectroscopy or vibrational rotational electronic spectroscopy. So this electronic spectroscopy is also called as UV visible spectroscopy, ultraviolet visible spectroscopy or vibrational rotational electronic spectroscopy is also, it is called. Why? Because, so I can explain later. See, listen. So if it is a sample, suppose we may imagine this is a sample. If the sample subjected to interaction with the UV visible range of radiation in UV visible spectroscopy, subjected to interaction with or subjected to interaction with the or passing through the electromagnetic range of radiation, if sample is interacted with the or irradiated with the electromagnetic range of radiation, or we can pass through the electromagnetic radiation, if this particular sample absorbs, suppose in UV visible in range of radiation, if it is sample absorbs UV visible range of radiation, we can pass electromagnetic range of radiation. If this sample particularly absorbs UV visible range of radiation, then this sample will give the UV visible spectroscopy, UV visible spectra or electronic spectra, UV spectra or electronic spectra, UV visible spectra or electronic spectra. What happened here in this case? This sample absorbs UV visible range of radiation, then it will give UV visible spectroscopy or UV visible spectra. That part is considered, that study in considered as UV visible spectroscopy. If this electromagnetic range of radiation is passing through the sample, suppose if the sample absorbs infrared range of radiation, that will be gives infrared spectroscopy. If it is electromagnetic range of radiation passing through the sample, suppose if microwave range of radiation, if it is absorbed, takes place, suppose by the sample, whatever the absorbed radiation which is there, that will be converted to the spectra. That microwave spectra which is obtained or rotational spectra which is obtained. Microwave or rotational spectra is obtained. So depending upon that, the electromagnetic range of radiation, is nothing but the which radiations is there? Which radiations are there? Radio waves are there, plus microwave radiations are there, and infrared radiations are there, and visible radiations are there, visible light is there, visible light, and ultraviolet light is there, UV light is there, ultraviolet light, and gamma rays are there, X-rays are there, gamma rays are there, like that. So rays will be there, different kind of rays will be there. So that means this electromagnetic range of electromagnetic radiation is an energy source which contains radio waves, microwaves, IR, visible, UV, X-ray, gamma ray, like that, which is there. gamma rays like that it may be there, cosmic like that it may be there. So if this electromagnetic range of radiation is passing, whatever the sample absorbs, IR, suppose infrared range of radiation, IR spectra, visible range of radiation, visible, like that ultraviolet visible range of radiation, UV visible spectroscopy, and X-ray like that. So here in this particular case, in the electronic spectroscopy case, this sample is interacted with the electromagnetic range of radiation, particularly absorbs UV visible range of radiation. So whatever the absorbed radiation, that will be converted to the UV visible spectra. Right? So that's what the electronic spectroscopy is also called as an UV visible spectroscopy. Because why? Because UV visible spectroscopy electromagnetic range of electronic spectra, because by the absorption of the UV visible range of radiation, only that spectra will give. So that's what this spectra is called as an UV visible spectroscopy. UV visible spectroscopy. Or this UV visible spectroscopy, why it is called as an electronic spectroscopy? What will happen after absorbing the UV visible range of radiation in the sample? If the sample absorbs the UV visible range of radiation, what is happening in the sample? In the sample, or it brings about changes in the sample while absorbing the UV visible range of radiation. What will happen? Changes in electronic energy levels. Electronic energy levels. Changes in electronic energy levels means what will happen? Electron will be redistribution takes place in different molecular orbitals. Electron is redistribution takes place. Electron distribution or redistribution takes place in different molecular orbitals. From ground, HOMO level to LUMO level, or from lower level to another level, it may be takes place. So electron redistribution takes place in different molecular orbitals. That due to that, what will happen? Changes in the electronic energy levels. Changes in the electronic energy levels. When changes in the electronic energy levels will be occurs, that spectroscopy is called as an electronic spectroscopy. Electronic energy levels will be changed. That spectra is called as an electronic spectroscopy. Electronic energy levels will be changed. So electron rearrangement takes place. That means electronic transitions takes place. During the electronic transitions, electronic transitions takes place. So that's what this spectroscopy is also called as an electronic spectroscopy. Right? Now, why it is UV visible vibrational rotational electronic spectroscopy? So I can explain later. See, listen. And I mentioned that UV visible range of radiation is absorption takes place. UV visible range of radiation absorption takes place. This UV visible general range is how much? Ultraviolet visible. UV means what? Ultraviolet visible radiation. Ultraviolet visible radiation. Visible range of radiation. How much this range of radiation is? 10 to 800 nanometers. 10 to 800 nanometers, that is considered as an ultraviolet visible radiation. In this ultraviolet visible radiation, 10 to 800 nanometers is there. This 10 to 800 nanometers also further it may be classified into that. 10 to 200 nanometers, whatever that, 10 to 200 nanometers, this is what? Wavelength. 10 to 200 nanometer wavelength of radiation which is there. That radiation which is considered as the for UV radiation or vacuum radiation. Vacuum radiation. For UV or vacuum radiation. What will happen? So this for UV radiation is the powerful radiation. Powerful radiation means more energetic. 10 to 200. Again 200 to 800 nanometers radiation which is there. 200 to 800 nanometers radiation, wavelength of radiation. What is that? Nanometer means wavelength of radiation. This wavelength of radiation which will be considered as the general UV visible range of radiation. General ultraviolet visible radiation. General UV visible range of radiation. We are using frequently in conjugated compounds, conjugated pi systems. Right? So this will be for UV or vacuum UV radiation will be used for particularly in the sigma electron system, saturated molecules case. In the sigma to sigma short transition case, we can use the 10 to 200 nanometers range of radiation. So I can explain later in which cases will be used for UV radiation or vacuum. So general UV visible radiation which will give. Particularly, and again this general UV visible radiation also, suppose this 200 to 400 nanometers radiation which is there. 200 to 400 nanometer radiation. This is called as the near UV radiation or quartz UV radiation. Near or quartz UV radiation. Near UV or quartz UV radiation. This 400 to 800 nanometers radiation which is there, 400 to 800 nanometers radiation which is there, this is considered as visible range of radiation. This range is which one? Visible range of radiation. So whatever the compound, if it is absorbs, this particularly absorbs suppose visible range of radiation, that compound which also exhibits color. If it exhibits color, which one? Visible range of radiation. If it is takes place, absorption takes place, that one is also exhibits the color. Suppose the beta carotene is an example. Having 11 double bonds is there. I don't write the structure. So having 11 double bonds are in conjugation in the beta carotene. 11 double bonds are in conjugation. So more number of double bonds are there and more absorption takes place while conjugation is increasing. Absorption of the lambda maximum is increasing. Why? Because I can explain later in the factors affecting the lambda maximum. So beta carotene having the 11 double bonds are in conjugation, which is going to be absorbs 451 nanometer radiation. The lambda maximum value is how much? 451 nanometers. Due to this visible range of radiation, if the absorption takes place, so this will be exhibits the reddish color. This compound which will be exhibits the reddish color. So because whatever the compound, if it is absorbs particularly visible range of radiation, that one is exhibits the color. Right. So this is the, and if it is from the sun to the earth, we can from the sun releases 10 to 800 nanometers radiation. So this 10 to 200, whatever that it may be the powerful radiation, powerful energy radiation, far UV or vacuum UV radiation which is there, that will be absorption takes place by the atmosphere only. So we can reach 200 to 800 that range of radiations to the earth like that. So now here in this case, the wavelength energy relation is what? Wavelength and energy relation is what here in this case? I can explain already 10 to 800 nanometers range of radiation which is there. The UV visible range of radiation. So general UV visible range of radiation which is the 200 to 800. And out of this 200 to 800, 200 to 400 is near UV and 400 to 800 is also visible and 10 to 200 is far UV or vacuum UV radiation which is there. So the energy sources for the near UV or quartz UV, near UV radiation or quartz UV radiation. So this hydrogen or deuterium discharge lamps will be source for the, what is the source for releasing of this radiation? Naturally, so hydrogen, which lamps are releasing? Hydrogen or deuterium discharge lamps. Hydrogen or deuterium discharge lamps. Deuterium discharge lamps will be releasing that 200 to 400 nanometers range of radiation. And this visible range of radiation which is there, whatever that the visible range of radiation, 400 to 800 nanometer range of radiation, that will exhibit, that will releases the source which is the tungsten filament lamps. Tungsten filament lamps or tungsten filaments which are releasing the 400 to 800 nanometers radiation. Now considering this wavelength lambda is the wavelength. So wavelength, which one is having more wavelength? 10 to 200 is lower wavelength, 200 to 400 considered to that compared to this more, and a 400 to 800 is very high compared to that range. That means lambda value, if you can take that, lambda of far UV radiation which is less, far UV radiation which is less, 10 to 200 is less compared to the which one? Lambda of near UV radiation. That is which one? 200 to 400 is less than to the which one? Lambda of visible radiation. That is which one? 400 to 800. This is how much? 400 to 800 nanometers, the units. And this is 200 to 400 nanometers. This is how much? 10 to 200 nanometers. Now what is that energy order? What is that energy? This is wavelength. Lambda is what? wavelength and energy is E. And energy and wavelength, which relationship is there? I already mentioned in the previous classes. The quantum mechanics point of E is equal to h nu is there. And you know that nu is equal C by lambda. Then that's what E is equal to hc by lambda. And energy and wavelength, which is inversely proportional relationship is there. So that means energy is more, wavelength is less. That means at lower wavelengths, more energy is available. So at higher wavelengths, less energy is available. Right? You understood? So if wavelength is less, more energy is available. More energy is available. Wavelength is high, less energy is available. So that's what energy order is. Which one? Energy of for UV, which is greater than, to the energy of near UV, which is greater than, to the energy of visible. Energy of visible radiation. Right? So that means 10 to 200 nanometers case, more energy is available. Suppose if the electronic transition required more energy, that will be available at lower wavelength case. Depending upon the molecular orbitals, energy level gap is also. Right? Further I can explain. Right? So this is the wavelength and energy relationship is there. Now, why it is UV visible spectroscopy is required? Why this UV visible spectroscopy is required? So many of the spectra are there. What is the use of this UV visible spectroscopy? Why it is again required? So depending upon the molecular energy levels, molecular energy levels, you know that the levels which are transitional energy levels are there, electronic energy levels are there, vibrational energy levels are there, and rotational energy levels are there. So depending upon the molecular energy levels, the energies of the energy levels. So transitional energy levels are there, are existing, and rotational, vibrational, as well as electronic energy levels which are existing. Right? Now these transitional energy levels which are not quantized, so we can use these quantized energy levels of these electronic, vibrational, and rotational, that it may be fixed energies which are there. So due to that, the electronic energy levels, that is quantized, vibrational, and rotational energy levels we have to use. A particular energy level having that molecule or atom which is there, or electron which is there, some fixed energy which is there, rotational, vibrational, and electronic energy levels. So that's for that it may be considered as the quantized energy levels. So we can take energy levels of the quantized electronic, vibrational, as well as rotational energies. So based on the energy of these energy levels, so electronic energy levels, energy will be more, electronic energy levels, energy gap will be more. So that means due to that, the energy is electronic energy levels, which is energy of the electronic level which is more compared to the vibrational, compared to the rotational. So that means, suppose this is an electronic energy level, E0 is an electronic energy level of the ground state, and E1 is the first excited electronic energy level, and suppose E2 is the second excited electronic energy level, and so on, which is there, depending upon that energy. Now, this electronic energy level, energy gap between the electronic energy levels which is more, that means electronic transitions which is required more energy, that is electronic energy, electronic levels energy will be more. So now here it is E0 to E1, this electronic energy levels, in between these two electronic energy levels, vibrational energy levels which will be arranged. So that means vibrational levels are possible, V0, this is ground state vibrational level again also. So between this electronic levels, vibrational levels are there, V1, V2, V3 up to dash Vx or Vn. Again it may be starts V0, V1, V2 up to dash, which is there Vx like that. Again V0 is going on takes place it up to that E3. So that means in between the electronic energy levels, vibrational levels will be arranged. E0 to E1 level case, which one levels which are there? V0 to Vx, all levels will be arranged. Right? So V0 to V1 and V1 to V2, V2 to V3 like that it may be there. V0 to Vx levels which will be arranged. That means compared to the electronic energy level, again it may be starts, again V0, V1, V2 up to dash, Vx, again V0 like that. So between the electronic energy levels, vibrational energy levels will be arranged. That means compared to the electronic energy level gap, E0 to E1, so this V0 to V1 gap will be very small. So that's what, when electron is excited from V0 to V1 required energy compared to this electron which is excited from E0 to E1, which is very high. So E0 to E1 is very high compared to this V0 V1, because this is lower energy there, less energy is required for V0 to V1, but E0 to E1 which is more energy is there. So that means in between the electronic energy levels, vibrational levels are arranged. Now this rotational, what will happen, rotational energy is still less. That means in between the vibrational levels, which one levels which are there? Rotational levels, R0, R1, R2 up to dash, Rx. Again R0, R1, R2 up to dash, Rx. Again R0, R1 up R2, Rx, like that it may be there. So that means in between the vibrational levels, V0 to V1, rotational levels are arranged R0, R1 up to dash, Rx. Again R0, R1 up to dash, Rx. So that means compared to this electronic rotational levels, rotational level energy gap will be small, then electronic energy level, then vibrational, then electronic. That means compared to the electronic energy levels, rotational energy, vibrational energy level energy gap will be less. Compared to this vibrational energy level gap, energy gap between the energy levels, rotational energy levels are still less. That means rotation takes place R0 to R1, very less energy is required. Then V0 to V1, more energy. Then E0 to E1, still more energy is required. So that's what like this. Right? Now, in electronic spectroscopy, that means UV visible range of radiation. That means in electronic spectroscopy, so the sample, what I can explain, the sample is absorbed in the electromagnetic range of radiation. The sample is absorbed particularly UV visible range of radiation if it is absorbed takes place. And what will happen after absorption of the UV visible range of radiation? The electronic energy levels will be rearranged. Electronic energy levels will be rearranged means what will happen? The electron will be redistribution takes place between the different energy levels. Electronic transitions takes place. So electronic energy levels will be changed. That means electron redistribution takes place from one energy level to one electronic energy level to another electronic level by absorption of the UV visible range of radiation. Suppose the absorption of UV visible range of radiation, what will happen? The electronic transition takes place from E0 to E1 or E0 to E2 or E1 to E2, like this it may be takes place. So what will happen? After absorption of the UV visible range of radiation, the electronic transitions takes place or electronic energy levels will be changed. That means the excitation takes place, the electron from E0 to E1 when it is transition takes place, or E1 to E2, this is the excited levels only takes place, or E0 to direct E2 takes place. So this type of levels will be takes place, this electronic transitions takes place. Now this spectroscopy I mentioned very beginning, this electronic spectroscopy or UV visible spectroscopy is also called as vibrational rotational electronic spectroscopy is also considered as. Why? Because when the electron, after absorption of the visible range of radiation, E0 to E1, if it is transition takes place, E0 to E1 transition takes place, in between these two levels, vibrational levels also there, rotational levels also takes place. That means if electronic transitions takes place, although this electronic transition which is accompanied with vibrational transition as well as the rotational transition, because between these two vibration levels are there, rotational energy levels are there. So that's what, when it is electronic transition takes place, this electronic transition which is already accompanied with, which one? Rotational as well as vibrational. rotational as well as vibrational. So that's what this electronic energy levels will be changed. Rotational vibration levels also involved. So that's what this spectroscopy is also called as rotational vibrational electronic spectroscopy. This UV visible spectroscopy or electronic spectroscopy is also called as rotational vibrational electronic spectra. Combine these three. Suppose in IR spectroscopy, if sample absorbs IR range of radiation, only V0 to V1 or V0 to V2 like that transitions takes place between the vibrational levels only. So if it is vibrational levels takes place, between the vibrational levels, which levels are there? Rotational levels. So that's what the IR spectroscopy, if it is there, infrared radiation absorption takes place, V0 to V1 takes place. Between the V0 to V1 or V1 to V2, which levels are there? R0, R1 up to the Rx will be there. That means rotational levels also involved. So that's what the IR spectroscopy, which is also called as rotational vibration spectroscopy also sometimes. Or purely is called as vibrational spectroscopy because vibrational energy levels will be changed like that. So if it is rotational, microwave range of radiation absorption takes place, only rotational energy levels will be changed, R0 to R1, R1 to R2 like that. So that's what that microwave spectroscopy is also called as a rotational spectroscopy because only rotational levels are involved, right? So like this, right? Now, whatever that if it is electronic transition takes place from E0 to E1, that absorbed radiation will be there, that absorbed radiation of the UV visible radiation, that absorbed radiation, whatever that absorbed radiation will be there, this absorbed energy radiation means absorbed energy radiation will be converted into UV visible band. UV visible band. Here, instead of signal, so I can, instead of sharp signals, broad signals will be possible. So that broad signals are broad peaks, which is considered as the band. Broad peaks will be considered, that broad peaks will be considered as band. That means instead of sharp signals are not identified in the UV visible spectroscopy. Instead of sharp signals, that will be considered as the UV visible band. UV visible band. So whatever that the observed radiation, that will be converted to an UV visible band. The position of the band which will be considered which one? See, listen. So in UV visible spectroscopy, we can record it whatever that the absorbed radiation, that based on that wavelength of the radiation, absorbed radiation, that means wavelength of the radiation in x-axis, and in y-axis percentage of absorbance, or we can sometimes we can use molar extinction coefficient, or epsilon maximum, or log 10 epsilon maximum. Sometimes we can use log 10 epsilon. So molar extinction coefficient or percentage of absorbance or epsilon versus wavelength of the radiation. That it will be considered as the UV visible spectroscopy. That means UV visible spectra. In spectra is recorded percentage of absorbance or molar extinction coefficient. By using that molar extinction coefficient, we can consider the intensity of the peak. That means nothing but the height of the peak, height of the band. So molar extinction coefficient or percentage of absorbance versus wavelength. So in UV visible spectroscopy, this type of broad signals will be possible. That broad peaks will be possible. Broad peaks. Instead of the sharp peaks, broad peaks will be possible. That means this peak, it may be suppose 200 to 250 nanometer range will be there, suppose. 200 to 250 nanometer range will be there. That starts with the 200 to 250 and with the 250. So what is the signal position? How you can take the signal position? That signal position you can consider as whatever that the position will be maximum absorption takes place, or maximum height is there, or maximum absorption takes place. That maximum absorption takes place, that is the highest point. Maximum absorption takes place, that it may be considered in terms of the molar extinction coefficient, that intensity. So maximum absorption takes place, that position wavelength which is considered as the lambda maximum. that one will be considered as the lambda maximum. So we can record, we can identify that position of the signal, that is the lambda maximum. Lambda maximum is position of the signal, that means position of the UV visible band. So we can identify that lambda maximum. Lambda maximum is what? Where this maximum absorption takes place, where that wavelength. So 200 to 250 nanometers range it may be there, absorption takes place. Out of this absorption radiation, where maximum absorption takes place, maximum intensity of the peak, it may be there, maximum absorption takes place, this position, that position wavelength which will be considered as the lambda maximum, that is the peak, that is the band of the UV visible band position. That position of the UV visible signal position will be considered as lambda maximum, that is which one? Maximum absorption takes place, where that it may be the maximum absorption takes place, that will be recorded as the lambda maximum. Now, I mentioned that instead of the sharp signals, broad signals will be appears. Broad peaks or broad signals will be appears. Why? Because broad signals are there. See, listen. I mentioned this electronic energy level, only electronic energy levels transition takes place in after absorbing the UV visible range of radiation. Electronic energy levels, we can identify that the UV visible spectroscopy point of view. Also, which is accompanied with which levels? Rotational, vibrational levels is also involved between these two levels. But the UV visible spectrometer cannot resolve every kind of vibrational transition is what? V0 to V1, V0 to V2. UV visible spectrometer does not recognize. That means does not resolve this rotational, vibrational levels. Although, which is not resolved, but due to the mixing of the or due to the merging of the rotational as well as vibrational levels, vibrational electronic levels in the electronic transitions, during the electronic transitions from E0 to E1 is already accompanied with the or merging of the vibrational and rotational levels. So due to merging of the rotational as well as vibrational levels in the electronic transitions, this peak appears will be as broad. Peak appears will be as broad. If vibrational spectroscopy or IR spectroscopy is there, only V0 to V1 if it is takes place, suppose V0 to V1 case, which levels are there? Rotational energy levels are there. So that's what in IR spectroscopy, like this, somewhat broadness is less compared to this. If it is rotational energy levels are only involved, so which can absorb in the microwave spectroscopy, sharp signals will be absorbed. Sharp signals in the microwave spectroscopy, in IR or vibrational spectroscopy, V0 to V1 takes place, already is accompanied with rotational levels also. That's what somewhat broad. In electronic spectroscopy, E0 to E1 is there, already accompanied with that merging of the vibrational as well as rotational levels. So this signal broadness will be more. So whatever that the broadness is there, the maximum absorption will be takes place. That will be considered as the lambda maximum. Suppose if we can consider, suppose for example, the maximum position, if it is in acetone, if it is there in acetone. So later I can explain the transitions clearly. What is in transition? How these transitions are possible, I can explain clearly. So I can explain only some of the basics here in this case, though basics also, but examination point of view, short questions which is there and it depends upon the basic points also. See, listen. In acetone, here the two transitions which are possible, pi to pi star transition, lambda maximum of the pi to pi star transition which will be possible 188 nanometer, and lambda maximum of the n to pi star transition, this lambda maximum of the n to pi star transition which is possible at 279 nanometers. 279 nanometers. Here two transitions are possible, pi to pi star and n to pi star. In addition to that, sigma to sigma star also, n to pi star and pi to pi star is possible. So why it is n to pi star transition? What is that meaning of n to pi star? How it will be possible? Which selection rules are governed? Or what is transition? Right? Which transitions are allowed? Later I can explain clearly. But though it is an example, just I can explain the lambda maximum position example like that. So in acetone, suppose this is 10 nanometer, 200 nanometer, and suppose 800 nanometer which is there. So here this type of signal which is possible, suppose suppose this is 250 nanometers or 230 nanometers if it is there, suppose. This pi to pi star transition which is possible at 188 nanometer. 188 nanometer. This one is considered as maximum band. Suppose this is the pi to pi star transition. Pi to pi star transition. So this pi to pi star transition band which is there, that will be absorbed at 188 nanometer. That means where that position maximum absorption takes place here in this position, that position will be considered as the maximum. So that position which is considered as which one? 188 nanometers. This position is the lambda maximum of pi to pi star. That will be considered as which one? 188 nanometers. 188 nanometers. One band which is possible, that is absorption of the band. UV visible band, that lambda maximum position of the pi to pi star, that is 188 nanometers. Another one. So another one which is possible at 279 nanometers, suppose here in this case 279 nanometers, another one band is possible, that band which will be N2 pi star, that is at 279 nanometers. 279 nanometers. How this lambda maximum value calculated also, Woodward-Fisher rules I can explain later. So N2 pi star transition, if it takes place 279 nanometers. So at 279 another one band is also possible. So compared to that intensities, this intensity will be more, this intensity will be less. Why? Because I can explain later. Right? So which factors are affecting, like I can explain. Why it is height, more height, which is less height. Although it is less height, more height, whatever that maximum absorption takes place, that will be considered as the lambda maximum. The position of this N2 pi star transition is which one? 279. The position of the pi to pi star transition in acetone, 188 nanometers, like this. If it is benzenite, benzene is there, 3 bands will be possible. Eclipse to are eclipsed bands, another one is benzenite band, lambda E1 at 180 nanometers, and lambda E2 band which is considered another eclipsed band, that it may be the 204 nanometers, another one benzenite band, if it is lambda B band, that it may be fine splitting is also there. So 255 nanometers, another one benzenite band is also possible. Like that is lambda maximum values. So that's what, like this, this position of the signals which is considered, right? So depending upon that, that's what I can explain. So what we are discussing here, the position of this, what is the spectra, which one in x-axis, which one in y-axis, and band, instead of 6 sharp signals, bands will be absorbed because merging of the rotational, vibrational as well as the electronic level. So that's what the spectra, rotational, vibrational, electronic spectroscopy also. And whatever the position maximum absorption takes place, that will be considered as the lambda maximum. And depending upon the energy of the electronic energy levels, depending upon the energy levels, electronic energy levels more energy, rotational is, vibrational is less still, rotational is still less. For example, this one I mentioned that. Now, so many of the spectra are there. UV, IR is there, microwave is there, NMR is there, and mass is there, mass spectrometry, right? Not spectroscopy, spectrometry. So now why? Because not mass is not spectroscopy, spectrometry. That means other than electromagnetic radiation, we are using as the energy source. So if electromagnetic range of radiation, we can use the energy source, that it may be spectroscopy. Other than electromagnetic range of radiation, that it may be mass case, we can use the electron bombardment takes place, so that it may be not in the electromagnetic range of radiation. So that's what, that it may be considered as spectrometry. Right? Later I can explain. So this one is, it may be there. Right? So why it is UV visible spectroscopy is required instead of so many spectra are there. So by using the UV visible spectroscopy, which information you will get, which information you will obtain, that is important. So many of spectra are there. Why UV spectroscopy is required? The importance of the UV spectra. What is the importance of the UV spectra? UV visible spectroscopy or electronic spectroscopy? UV visible, ultraviolet visible or electronic spectra? What is the importance of electronic spectra? Electronic spectra or UV visible spectra. So this is mainly used for the detection of the chromophore. Detection of the chromophore. So ultimately all the spectra's main use is whatever the spectra, UV visible spectra or IR or microwave or NMR or whatever it, proton NMR or CTN, whatever it may be, all the spectra's or the spectroscopy's main aim is what? To determine the, if it is an unknown sample, if it is there, this unknown sample structure you don't know that. So if you don't know the structure, you don't know the properties. You don't know the properties. So that's what. So if it is an unknown sample, if it is there, that unknown sample structural elucidation is first important. Structural elucidation is first important. For this unknown sample, structure will be determined how? By using the spectroscopy. By using the spectroscopy. Spectroscopy is used not, why? Because to know the unknown compound or unknown sample structure in the structural determination of the unknown sample. Once you know the structure, then you know get the properties of that compound, which one properties which is there as an optical active or inactive or so many properties. During the structural elucidation, one type of spectra will give some information, one type of information. Proton and NMR spectra, different kinds of protons, and IR spectroscopy, different which kind of functional group is there, right? And rotational spectroscopy is there depending upon the bond lengths and masses. And mass spectrometry is there, that it maybe depends upon the fragments, mass spectrometry like that. So one kind of spectra will give some kind of information. Similar like this in the structural elucidation point of view. Similar like this in the UV visible spectroscopy will gives the detection of the chromophores. It gives the detection of the chromophores. How this detection of the chromophores? By depending upon the lambda maximum. That means UV visible band, the band positions. So if it is chromophores, detection of the chromophore. What is chromophore? What is chromophore? Now, chromophore is what? The importance is what? To detection of the chromophore is simply. But what is chromophore? If it is a compound or if it is a substance which is there or a species which is there or a group which is there, if it is a group or species which is there, this group, if it is capable to absorbing directly UV visible range of radiation, that general UV visible range of radiation of 200 to 800 nanometers range of radiation, if this radiation will be absorption takes place directly, right, or directly, right? So our group which is capable of absorbing 200 to 800 nanometer range of radiation, that one is called as, that group or species which is called as the chromophore. If it is capable to absorbing 200 to 800 nanometer range of radiation. Suppose diene is a chromophore. Diene is a chromophore. Diene is a chromophore. Diene is a chromophore. This is a chromophore. Why? Because this conjugated pi system of this chromophore, this conjugated pi system of the chromophore, saturated pi system is there, that it may be saturated system is there, only saturated molecule is there like that ethane, like that methane, that it may be not capable to absorbing this radiation 200 to 800, but it may be there 10 to 200, right? But general UV visible range of the 200 to 800 nanometer radiation, if it is capable to absorbing, that one is called as the chromophore. Conjugated chromophores are which one? Conjugated pi systems. Which systems? Conjugated pi systems, pi electron systems. Conjugated pi systems act as the chromophores, or the pi electron system or double bond or pi electron system containing, or pi systems or double bond systems containing lone pair of electrons. Containing lone pair of electrons, or double bond or conjugated system containing the lone pair of electrons. Conjugated system having the lone pair, or pi electron system containing the lone pair, or conjugated pi electron system which is considered as the chromophore, because that systems are capable of absorbing this radiation, 200-800 nanometers radiation. Only saturated molecule which is there, it is not that. Why? Because it is not capable of absorbing this radiation. So this radiation capable of absorbing, that is considered as chromophore. Like this, diene is a chromophore. How much lambda maximum is there? 217 nanometers, this lambda maximum of pi 2 pi star. So that's what, that it may be capable of absorbing this range of radiation, so that is chromophore. And enone is also a chromophore. Enone chromophore, like this, 237 nanometers which are there, 231 nanometers which are there. And carbonyl is a chromophore. This is also capable of absorbing UV visible radiation. Only double bond is there. In addition to double bond, lone pair of electrons which are there. Simple or isolated double bond which is not that chromophore in some of the case, but when it is in addition to that in addition to that double bond, pi electron system having lone pair electrons are there. Pi electron system having lone pair of electrons, or conjugated pi systems like that. Is a chromophore. Or thiocarbonyl is a chromophore. Thiocarbonyl, C double bond S. Nitro is also a chromophore. Nitroso is also a chromophore. Or azo is also a chromophore. Azo is also a chromophore. Or aromatic chromophores which are there. Benzene, naphthalene, like this aromatic chromophores. Which one is aromatic chromophores? Benzene, naphthalene, anthracene, like that, which is also considered as the chromophores. Aromatic chromophores are also there. So whatever that, it may be there, conjugated pi system or double bond which are having lone pair of electrons which are there, that it may be considered as chromophore. It is capable to absorbing the UV visible range of radiation. So the detection of the chromophores, this chromophores will be detection takes place by using the UV visible spectroscopy, by considering the UV visible band positions. UV visible band positions, we can identify that. So you know that the term chromophore, you know that the term chromophore. Another some of the terms which are there, we are using frequently in the UV visible spectroscopy or electronic spectroscopy. Which term is again we are using, I can explain. Here in this case, another one term is auxochrome. We are using frequently auxochrome. Chromophore, you know that. What is chromophore? You know that. What is an auxochrome? What is an auxochrome? See, listen. Here, these groups are directly absorbs the UV visible range of radiation. Here, auxochrome groups are. What is that auxochrome groups? This type of auxochrome groups directly cannot absorb the UV visible range of radiation. It is not possible to direct absorption of UV visible range, which is not possible. Directly cannot absorb the UV visible range of radiation. But independently, how this independently? That means directly cannot absorb the UV visible range of radiation. That means independently, which is not capable to absorb the radiation. Independently cannot absorb the radiation. But whenever this group is attached to the chromophore, that group which is attached to the chromophore, due to this group, the absorption wavelengths of the chromophore will be increasing. Absorption wavelength of the chromophore will be increasing. Indirectly it will be affects the lambda maximum, but directly which is not there, directly which cannot absorb. So that group which is called as oxochrome. See, listen. Oxochrome directly cannot absorb the UV visible range of radiation, but whenever this oxochromic group which is directly attached to the chromophore, due to this group, this chromophore lambda maximum enhanced. That means due to this group is attached to the chromophore, it will enhance the lambda maximum or wavelength of the chromophore, that group or species which is called as an oxochrome. Now, which one groups are oxochromic groups are there? Which one groups are considered as oxochromic groups? Electron excessive groups, electron excessive species, or lone pair electron species, the groups having lone pair electrons, or negative charge groups. Suppose OH is having lone pair of electrons are there. Electron excessive groups, more number of electrons are, this is an oxochromic group. Suppose NH2, lone pair of electrons are there, it is an oxochromic group. Or NHR is an oxochromic group. Or O is an oxochromic group. Right? So many of these oxochromic groups which are there like this. S or Thio is also a oxochromic group. SR is oxochromic group. Or O minus is also a oxochromic group. Or NH minus, instead of NH2, NH minus, which is there, negative charge is also there, that is also oxochromic group. Or S minus is there, that is also, it may be considered as an oxochromic groups. Right? All this which will be considered as an oxochromic groups. What is the nature of the oxochromic group? Directly, which cannot absorb UV visible range of radiation. That means independently not possible to absorb UV visible range of radiation. But whenever that is attached to the chromophore, whenever that oxochromic group, particular oxochromic group attached to the chromophore, it will enhance the absorption wavelengths of the chromophore. It will enhance the absorption wavelengths of the chromophore. See, listen. Absorption wavelengths of the chromophore. I mentioned that aromatic chromophore, benzene is an chromophore. Benzene is as an aromatic chromophore. In this benzene, the lambda maximum of benzenite band, lambda B band is benzenite band, is 255 nanometer. It is a chromophore. Whenever this chromophore, if it is attached to the oxochromic group, this group is which one? OH group is oxochrome. Whenever this oxochrome group, OH is an oxochrome group, electron excessive species or negative charge species considered as oxochromes. Like that, lone pair of electrons which are the electron excessive, lone pair electron species or negative charge species. So here it is, when this oxochromic group which is attached to the chromophore, directly which is not absorbed, but whenever it is attached to the chromophore, whenever this group is attached to the chromophore, it will enhance the absorption wavelengths of the chromophore. Before this chromophore absorption wavelength is 255, after attached to the oxochromic group, this lambda maximum of benzenite band which will be enhanced to the 287 nanometers. 287 nanometers. What will happen? 255 to 287 nanometers will be increasing. So due to this lambda maximum of the chromophore is increasing. So this is called as an oxochromic group. Oxochromic group. Right? Oxochromes are, you know that. Chromophores are, you know that. Another terminology is also there. Further in the UV visible or electronic spectroscopy point of view, bathochromic shift. Bathochromic shift. What is that bathochromic shift? Bathochromic shift is which shift? And hypsochromic shift is also there. Bathochromic shift, hypsochromic shift, which is there. Right? Bathochromic shift, or also sometimes this shift is also called as red shift also. What is bathochromic shift? Bathochromic shift means shifting of position of UV visible band, shifting of position of UV visible band, whatever that the position of the UV visible band is there, lambda maximum band. This shifting of this position of the UV visible band or position of the UV visible band or position of this UV visible band shifting towards right side of UV visible spectrum, or shifting towards higher wavelength side of the UV visible spectrum, higher wavelength or right side of the UV visible spectrum. That is considered as bathochromic shift. That is considered as which shift? Bathochromic shift. Suppose I mentioned this, the above example, in the case of the aromatic chromophore of benzene, what will happen? 255 to 287 nanometers. So, which is related to the epsilon maximum or log 10 epsilon maximum or percentage of absorbance, and this is the wavelength lambda. So this lambda maximum band, lambda maximum of benzenite band, 255 nanometers. 255 nanometers, lambda maximum of which one? Benzenite band. Right? When this band, this position of UV visible band shifting towards right side or higher wavelength side. Right side means like this side. So after that, what will happen when it is attached to the oxochrome? This will be shifted to the 287 nanometers. 287 nanometers. That means shifting towards the higher wavelength side. So if it is lambda wavelength is there, this is lower wavelength, this position is higher wavelength. Shifting towards higher wavelength side. This position, lambda maximum position 255 nanometers, when it is shifted to the 287 nanometers, right side will be enhanced takes place. Right? So that's what the higher wavelength means. Lambda maximum is what? Increasing. Lambda maximum is increasing. That shift which is called as an bathochromic shift or red shift. This side, this one is called as right side. This position of visible band shifted to the right side or higher wavelength side. Right side or higher wavelength side. This shift is called as which one? Bathochromic shift. Bathochromic shift. This example is a bathochromic shift. Which shift this is? Bathochromic shift. Shifting towards right side or red shift. Next, another one. Hypsochromic shift. Another one shift is which one? Hypsochromic shift. What is hypsochromic shift? This is up or blue shift. This shift is also called as hypsochromic shift or blue shift. This is opposite to this. This one, bathochromic shift, position of the UV visible band shifted towards right side or higher wavelength side. Now here it is position of UV visible band, that is which one? Lambda maximum. Position of UV visible band shifting towards which side? Left side. Which is shifting towards left side or which side? Right side is higher wavelength side. This direction. This direction is lower wavelength side. Lower wavelength side. Shifting towards lower wavelength side. Lower wavelength means what will happen? Lambda maximum position is decreasing. Lower wavelength side. That shift is called as hypsochromic shift. Right side or higher wavelength is bathochromic. Left side or lower wavelength is hypsochromic shift. Hypsochromic shift. Like this. Epsilon maximum, nothing but the intensity or log 10 epsilon maximum. And this is the wavelength. Here in this direction is more. Now, this wavelength, if it is band, if it is like this lambda maximum band, if it is there, this band is shifting towards lower wavelength side. Lower wavelength side. This lambda maximum is shifting towards lower wavelength side. This shift is called as which one? Hypsochromic shift. Hypsochromic shift towards lower wavelength side. For example, I can give one example for this hypsochromic shift also. Hypsochromic shift. I can give one example. Which one is considered as hypsochromic? Is opposite to the bathochromic, right? See, listen. Just before I can explain, acetone in presence of N-hexane. N-hexane means which one? Non-polar solvent. If it is a non-polar solvent, acetone will be taken in non-polar solvent. Acetone pi 2 pi star and 2 pi star both will be possible. I can explain what is an transition means. So the lambda maximum of which one? N2 pi star of acetone is 279 nanometers in non-polar solvent. Non-polar solvent. If it is the same one, if it is this acetone will be taken in polar solvent of whatever that, if it is methanol will be taken, suppose methanol in polar solvent due to the attractions, due to some interactions. Later I can explain the solvent effect, what is the solvent effect on the absorption maximum, lambda maximum position. Later I can explain the factors. But randomly I can explain the hypsochromic shift. So in the case of the polar solvent, this lambda maximum of N2 pi star, which will be 270 nanometers. 270. That means 279 to 270. That means what shift this is? Lambda maximum is decreasing. Lambda maximum is decreasing. This shift is called as which one? Hypsochromic shift. Hypsochromic shift. That means in N2 pi star transition in polar solvents, non-polar to polar, that shift is hypsochromic shift. Non-polar to polar, that shift is hypsochromic shift. Towards the right side. Sorry, towards the left side or lower wavelength side. 279 if it is there, 279 to 270. That is hypsochromic shift. Another two shifts which are there again. Another two more shifts which are there. This one is hypsochromic shift or blue shift. Another two shifts are there. Hyperchromic shift, hypochromic shift. What is that? Hyperchromic and hypochromic shift. Hyperchromic and hypochromic. So that too is also there. I can explain in one line. That too also we are using further frequently. Hyperchromic shift and hypochromic shift is also there. So hyperchromic shift, which is related to the, which is depends upon the intensities of the band. Intensity of UV visible band. Intensity is nothing but the height of the UV visible band, depending upon that. So epsilon maximum, if it is considered as the intensity or log 10 epsilon maximum, and this is wavelength. Suppose this is the band, if it is there, this is the lambda maximum. Now here in this band, if it is this intensity of the band which is shifted to the higher side, that it may be going to be, this position is going to be here in this direction. So that means before here in this position, epsilon maximum, after that this position, that means epsilon maximum is increasing. This is the band before. When it is increasing, this intensity will be increasing. Intensity of UV visual band or height of the UV visual band, it is enhanced or increases. intensity of the UV visible band increases, nothing but the epsilon maximum of the UV visible band increases, nothing but the height of the UV visible band. Absorption position will be increasing. This position to this position towards the upper side. This one intensity of the UV visible band or epsilon maximum is increases. This shift is called as which one? Hyperchromic shift. Hyperchromic shift. This one is hyperchromic shift. Hyperchromic shift. Now, another last one shift is hypochromic shift. What is that? It is also related to the intensity of the UV visible band. Intensity of the UV visible band, if it is decreases, intensity is measures, nothing but the epsilon maximum is measures the intensity, that it will be decreases. That shift is called as which shift? Hypochromic shift. See, listen, the epsilon maximum or log 10 epsilon maximum and lambda if it is there, before like this if it is there, lambda maximum position, after then it may be decreasing. So like this, lambda epsilon maximum is before, after then it may be there, decreasing towards the downward side. This will be considered as hypochromic shift. In one word, all those can be explained. Lambda and epsilon maximum or log 10 epsilon maximum wavelength. If it is the band, if it is there, band position, the lambda maximum is shifting towards right side. That shift is which one? Bathochromic shift. Is shifting towards left side or lower wavelength side. This one is called as which one? Hypsochromic shift. Hypsochromic shift. When epsilon maximum intensity, when it is increasing, height of the band will be increasing or intensity of the band will be increasing. That is nothing but which one? Hyperchromic shift. When it is decreasing, intensity or epsilon maximum, that is which one? Hypochromic shift. Right? You know that the four shifts. You know that the four shifts. Later I can give the examples also in next classes, coming classes, in the factors also, which factors are affecting the epsilon maximum I can explain. So depending upon that epsilon maximum, which factors are affecting, height, in which case it will be more height, which case will be less height, like that. Epsilon maximum is more in which case is less. That will be also we have seen in the next class, coming class. This is the four kind of shifts which is there. In the later class, this UV visible spectroscopy point of view, we have to use mainly how this chromophores will be detection takes place. To detect the chromophore, how? Based on the lambda maximum. How this lambda maximum is obtained? By the electronic transitions, by absorption of the electron, by the absorption of the radiation, electron transition takes place. Whatever that radiation will be converted to the absorption of the UV visible band. So that's what the electronic transitions also necessary in UV visible spectroscopy or electronic spectroscopy. Electronic transitions are necessary. So in next class we have seen the what is an electronic transition, what is a transition or electronic transition, which type of transitions which are there for depending upon the molecules, type of molecules, for which molecule which type of transitions are possible. Out of the transitions, which transitions are allowed, which criteria will be there, symmetry or multiplicity or energy, which criteria will be allowed, which one transitions will be allowed, which one will be forbidden. In next class we have seen. Right? Thank you.